Good morning, Astronomy 1010. Welcome to Lecture 2, Part 2, where we are going to learn more about the local sky and a wee bit about timekeeping and planetary orbital periods. We'll also be doing homework number 2 today, which are problems from Chapter S1, special Chapter S1 on timekeeping, celestial navigation, and some other miscellaneous things related to the local sky. Interesting stuff. I thought I would begin today by trying a couple of exercises which attempt to train you on using two of the coordinate systems that we learned in our last lecture. We learned the horizon system, which measures the position of a star in terms of altitude and azimuth. We also learned about the equatorial coordinate system, which is sort of a latitude and longitude for the sky, and it pegs the position of a star with right ascension and declination. Our labs used those coordinates a bit, but it's a different kind of thing when you have to kind of imagine a problem in your head, as I am about to demonstrate. Let's start by practicing the horizon system. And we're going to do a little game here where we make a 2D view of the local sky, which is a great technique to do if you're having to solve problems during an astronomy exam. Let's grab our rulers. Let's make another 10-centimeter line halfway down the page. Mark the midpoint at 5 centimeters. Also mark the radius at the top of your dome. So make a 5 centimeter distant dot at a few key places. That'll help you sort of draw in the dome of your sky. I'm just going to do a 3-dot system today, and then I'll just sort of connect the dots. Not a shabby looking 2D dome there. Even though I'm not making this 3-dimensional, I'll kind of shade down here so that we understand this is the ground. Okay. I will place an observer at the center of the field. Where should we put north and south? We're going to make a north-south slice of the local sky.
So north will be to the right.
Yes, that's customary to put north on the right and south on the left. By the way, I've been noticing in the recordings that my voice is a little loud, and I wonder if I shouldn't just take that microphone down a little bit. Let me know if you have trouble hearing me. I'm testing myself, sorry. I think it's better to be a little too loud than quiet, but we'll see. Okay, I just notched it down a smidge. Okay, let's draw a line up through the top of the dome. And we'll mark it with a Z for zenith. And let's assume it's a northern local sky, or since we are, after all, Rhode Islanders for the most part, we'll do a 2D view of the Rhode Island local sky. And I will draw in a north celestial pole somewhere on the northern sky. Don't forget that the dome is your sky here. We're piercing the sky, so I can label north celestial pole. That's, of course, where Polaris is. Now, we will make a 90-degree angle here. This is a line that will point towards our celestial equator. see here if I can take the lights down a smidge. It seems dark in my place, but that's probably a little better for your screen. Okay, I'm now going to take a green marker and I'm going to label. There are 4 angles that you can see here on the board. And I will label these angles alpha, beta, gamma, and delta. Those are the first 4 letters of the Greek alphabet in honor of the Greeks who loved geometry. Alpha, beta, gamma, delta. Let's try a few sample problems. One of these angles is a direct representation of your latitude on Earth. Which angle represents your latitude? Who'd like to try that? Of the 3 people who are sharing video with me, you guys are getting dangerously close to getting pre-recorded lectures. I want you to know that, okay? If you're going to do this to me, then you can just watch the fucking video and give me some time off, okay? Alpha, beta, gamma, delta. Which one of these represents the latitude on Earth?
I'm going to guess alpha.
Not alpha. Why don't we start by reading the definition of latitude based on your lectures last time. You should have some lecture notes. Whoever said that to me. Who was just talking to me?
Oh, that was me. I was trying to find it. It says degrees north or south of the equator.
Okay, so based on that, which of these angles might represent degrees north or south of the equator? So you said alpha. Alpha is not the correct answer, but I guess I have to tell you the correct answer to. Let's try to imagine drawing an Earth down below, okay? So I'll take this Frisbee and I'll try to draw Earth in such a way that the observer is in Rhode Island, the equator is maybe here. Okay. So let's imagine that the equator of Earth is pointing in this direction. So there's the equator. And the North Pole is like so. And I'm drawing this because I want the Rhode Island observer's head to be pointed up. So since we're kind of halfway up the globe, I need to draw a line from the center of the Earth pointing up that hits Rhode Island. If Rhode Island has a latitude of, so here's your observer actually. Now, what did you say again, Cole? The definition of latitude?
Degrees north or south of the equator.
And are we north or south of the equator?
We're north of the
So
equator.
that means this angle here from the equator up to us is our latitude, degrees north. Does that help us at all?
Yeah, so it'd be beta.
That's right. Beta is your latitude, and you can see why. The reason why is that your feet and your head point towards the zenith. That's your location on Earth. But the equator points towards the celestial equator. So the angle between the celestial equator and the zenith is the same angle as the angle between your equator and your feet, right? Beta is your latitude. And what is the latitude for dear old Providence, Rhode Island? I also gave you that last time. Or should
42 degrees north.
42 degrees north. So beta then in our diagram for Rhode Island would be 42 degrees. That's why I put myself about halfway. 42 degrees is dangerously close to a 45-degree angle. So we should be halfway between equator and North Pole by logic. Okay. So having drawn that, the answer to number one is beta. One of these angles, alpha, beta, gamma, delta, is a direct representation of the altitude of Polaris. Which angle here represents the altitude of Polaris? You may want to regurgitate the definition of altitude.
Gamma.
What's the definition of altitude?
Degrees above the nearest horizon.
Okay. So if Polaris is there, what's the nearest horizon?
Delta. It's the bottom down below.
Yeah, actually, I've got a question for you, class. Where is the horizon in this diagram? Where's the horizon?
Is it the bottom line, the one that we're standing on, like the north to south?
That's the ground.
No, that's the top.
The Z.
No, it's at the top. I want you to be really fucking specific here. I don't want you to be like kind of like it's over there somewhere. The horizon is a three-dimensional ring. We are drawing a two-dimensional slice. Our horizon penetrates this illustration that we made in 2 points, in 2 places. Here's the 3D view of our local sky for reference. For those of you who don't remember or understand, this ring, this is your horizon ring. This is not the horizon, that's the ground. So where does the horizon intersect this diagram?
All of the points.
You're not loud enough for me to hear you.
Is it all of the points? Because like south, north.
All of the points, like, I don't even know what that means. These are all points, like the whole thing.
Um,
Z.
No one's saying this.
It's,
well, on the last diagram, it was you showed the horizon. And it was intersecting
Intersecting where?
this. I don't know how to explain it.
Well, yeah,
Um,
this is part of the game, right? Is trying to talk the talk.
Is intersecting at northeast, southwest.
Northeast does not appear in this diagram. This is a purely north-south line.
So north and south.
Due north
Mm,
and due south.
yeah.
The horizon intersects here at due north. That's your northern horizon. And the horizon intersects here at due south. That's your southern horizon, right? Okay, so anyways, what's the answer to the question? The altitude of Polaris is wow, I've just spun you guys all around and you don't know what's what.
oh, sorry, alpha, beta, gamma. Yeah, delta.
Delta.
I was thinking delta, yeah.
Because the definition of altitude is the degrees between your star and the nearest horizon, which is the northern horizon. So this is the altitude of Polaris. Got that down. Now, I spy with my little eye a 90-degree angle. The 90-degree angle is between the north celestial pole and the celestial equator. That makes sense to me because there's a 90-degree angle between the equator and the North Pole, which means gamma must be what angle? Oh, by the way, make sure you write this down in your notes. Delta. It's the altitude Polaris. That's the
45.
nope, not 45.
If wait, what did you say was 90 degrees? Oh,
Celestial equator to North Celestial Pole is 90 degrees.
Would it be 48 degrees?
It's 48 degrees. Why? Explain that to the public.
Because it's a 90-degree angle, so you should just subtract 42 and it gives you 48.
That's right. If beta is 42, gamma must be 48. I spy with my little eye another 90-degree angle. There must always be a 90-degree angle between the zenith and the horizon, meaning delta must be what?
42.
42 degrees. And for completeness, what would alpha be then?
48.
48 degrees. Huh. Now, these angles are the angles in question for a Rhode Island local sky. However, wherever you go on Earth, there you are, as Buckaroo Banzai says. And, you know, there's always going to be a 90-degree angle between the zenith and the horizon. There will always be a 90-degree angle between the equator and the North Pole. And therefore, beta will always be equal to delta wherever you go. And that means we have proven a fundamentally useful result. And the useful result goes like this. The altitude of Polaris is equal to your latitude. Oh, shoot. I forgot. My friend is trying to sit in on these lectures, and I keep forgetting to send her the damned link. I knew there was something I was forgetting. This is a very important result. This result is so important that we should put an exclamation point next to it. We should put a box around it. We should put some stars next to it, and we should cover it with beams of fire so that it is impossible to miss in our notes. It's such a useful result, and it can help you solve many questions on an exam. Why don't we try a question from our homework today, which will save double, triple time. So here's an in-class question. The question would be, describe the location of Polaris in the Rhode Island local sky. Well, what's the answer?
Polaris is the same latitude.
Huh? I'm sorry, could someone say that? Who's that talking? Because your microphone is so loud. It sounds like you're talking like this. I can't really hear you.
Sorry, I would just said that Rhode Island's latitude is the same as Polaris, which is just, we're describing the location of Polaris. So if what you said is true, then it has the same latitude. Then what else would I say about this?
Well, okay, here's what you're missing. last class, I taught you a coordinate system to properly describe the position of an object in your local sky. What is that coordinate system called?
The
The
horizon.
horizon.
Great. We are going to use the horizon system to answer this question. Use the horizon system. And what two angles do we use in the horizon system?
Altitude and azimuth?
That's how we answer this question. See, you guys didn't even understand what I was looking for, or not at first, but now you do. I was waiting for you guys to give me an altitude and an azimuth, because that is the proper way to talk to me when describing the position of a star in my local sky. So, find the location of Polaris in the Rhode Island local sky. I'm looking for two numbers here.
So would the altitude be 42 degrees?
Booyah! Booyah! Someone's paying attention. 42 degrees is the altitude. Now, what about the azimuth? I'm going to have to remember what azimuth means, and I can't remember what azimuth means. Maybe I should look in my notes.
This
The
is
azimuth is 0.
Whoa, who said that? Who knows what's going on? I'm impressed. Who's talking to me?
Michelle.
Michelle is correct, because azimuth is defined as your degrees along the horizon, measured clockwise from north. Now, we could say 0 degrees. That's perfectly valid. Or we could also specify a direction, north, because north is a type of azimuth. That's how we talk. We say Polaris is 42 degrees above your northern horizon. That's the horizon system. Let's try another question, a more advanced question. I guess I'm going to have to erase this, so make sure you got that down. May I erase, or does someone need a second? Question number 2. Describe the path of the celestial equator in the Rhode Island local sky. I'm just going to write sky because I ran out of blackboard space here. Describe the path of the celestial equator in the Rhode Island local sky. Now, here, I should throw y'all a bone and show you the 3D view of our local sky. So hopefully you guys recognize that the celestial equator is here, right? It's this line here, right? Or this arc, I should say. This might be a little more complicated. Unlike Polaris, which was located at a point, the celestial equator is an arc or a semicircle that arcs through your sky. And therefore, a single altitude and azimuth is not sufficient to describe its trajectory or its path. Instead, we should choose 3 points to describe its path. The point where it rises, the highest point in the sky it reaches, and the point where it sets. So we are going to use 3 points to describe this arc, the 3 orange dots that you see. So let's write this down. It's an arc. And that means 3 points are needed, all using the horizon system. We want the point where it will rise, the point where it reaches its highest in the sky, and the setting point. And each one of those points will have an altitude and an azimuth, meaning 6 coordinate locations, or 6 numbers. 3 coordinates, but 6 numbers. Okay, AS1010 Live, you're up. Let's start with the rise point. How do I describe the altitude and the azimuth of this point? It's the altitude and the azimuth of the orange dot. Use your skills, use your noodle.
The azimuth would be east.
Okay, I would accept east as an azimuth, Daniel. That would be fine. Could you also tell me the numerical azimuth as well, so that we can see that there's 2 different ways to do this?
According to my notes, it's due east, so it's 90 degrees.
Good. What would the altitude of that point be, Daniel, since you're doing so good?
Let's see, altitude.
This is about vocabulary here.
Yeah. So I'm assuming it would be 0.
Yeah, it's on your horizon.
Mm-hmm.
So boom, its altitude is 0. Very good. Very good. So it's 0 degrees east, or that's actually the same as saying due east. Due east is a way of saying east on your horizon. Let's try the reach point. The reach point is the highest the celestial equator will get in our sky, which looks about there. What is the altitude and azimuth of the orange dot?
Would it be 48 degrees due south?
Okay, it would be 48 degrees in which coordinate?
Altitude?
It would be 48 degrees altitude. And yes, the azimuth is south, but you cannot say due south. Due south to me means this point on the horizon. That's a confound that's confusing because our point is not on the horizon, but it's pointed up there. So you could say 48 degrees south, but I would avoid saying due south. So
Okay.
48 degrees south. And what's the technical azimuth of south?
180.
That's right. And then now that you're starting to understand, what would be the setting point of the celestial equator? Here.
0 to 70, 0 degrees, and then to
Sure.
70.
0 degrees altitude.
Yep.
And the azimuth would be west, or 270 degrees. And whoever I was talking to before, because it's not always obvious sometimes, that would be due west because it's on the horizon. That's the proper way to do this. Suppose you wanted to answer this question, but you wanted to be literary about it. You wanted to be literary, but not a confusing moron or something. you would say, I almost want to write this down. The celestial equator is an arc that rises due east, reaches an altitude of 48 degrees in the south, and sets due west. That would be an elegant phrase that contains all of the power of the horizon system, all the specificity. It's not ambiguous. That's what we like the horizon system for. Nice. Very good. Okay, so that should have been a good learning exercise for you. I'm going to erase all this now. What if we wanted to test ourselves with the equatorial system? I did this with my 1020 class, not with you, but I think it's such a good idea that I'd like to do it. Let's sort of describe the equatorial coordinates, the right ascension and declination of the 4 key points of 4 key points on the celestial sphere. Spring equinox will have a RA and a deck. The summer solstice RA deck. The fall equinox RA and deck, and the winter solstice RA deck. This ought to be a little bit of a adventure. Let's grab a picture of the celestial sphere. Okay, this one's tilted so that the north celestial pole is over here on, it's tilted by 23.5 degrees. So up here, that's the NCP. Okay. Oops. Let's start with this point. We need a right ascension and we need a declination for this point. Someone want to regurgitate the definitions for us? Ente, I'm glad you're sharing video with us, if I'm saying that right. Maybe you can read us those definitions. Do you have them?
Yeah, it's John. Sorry.
Okay. Okay.
You talk about the declination, right? Ascension definitions.
Please, sir.
All right. Declination is the degrees plus or minus from the celestial equator.
Yep.
Yeah. Right ascension is the hours and minutes measured eastward from the spring equinox.
All right. So we measure right ascension like so. We measure declination like so. The celestial equator is the red line. So what do we think? John or anyone else? I need a right ascension or a declination of this point.
Wouldn't the right ascension for that point be 6 hours?
Well, we measure right ascension. Do you understand that the vernal equinox is the same thing as the spring equinox? Maybe that's what's going on.
Oh, okay. Well, in that case, it would be 0 out.
That's right, because you're on the spring. All right, so that's what it was. You guys didn't understand. The vernal equinox is the spring equinox, right? So you're on the spring equinox. So yes, it's 0 hours is how we would do that. Okay. How about the declination? We always do right ascensions like a sort of military time there. The declination?
0 degrees.
Yeah, because you're on the celestial equator. Very good. Okay, how about the summer solstice?
.6 hours.
Yep, you're a quarter turn, so you're 6 hours. How about your declination?
23.5 degrees.
Yep, that's how many degrees above the celestial equator it is. We say positive, so 6 hours and positive 23.5 degrees. Fall equinox.
Would it be
That would
12
be-
hours right ascension and then a 0-degree declination?
Beautiful. Now you guys are getting me. So the RA would be 12. The deck would be 0 degrees. And the winter solstice?
That would be 18 hours at negative 23.5 degrees.
Beautiful. Nicely done. Okay, so there's some real differences between the equatorial system and the horizon system. They're used in different ways. You know what's really confusing? What's really confusing when you try to start doing the equatorial system on your local sky. That's when things get a wee bit messy. Got a couple of slides on that, not great ones. Really wish that I had a better slide for this. Hold on a second here. Oh, all the little Zoom things are in my way. Everything's in my way. That's, of course, the one that I need. Okay, this picture, sorry, not this picture. An illustrator in this picture has attempted to put the equatorial coordinate system onto an observer's local sky in the northern hemisphere. Now, first, you've got an observer. Now, of course, they did this in a kind of funky 3D way. I would have preferred north. Oh, they did, sorry, north is to the right for once. So here you can see the north celestial pole is pointed up there, and that means their celestial equator is pointed in that direction. Looks to me like this observer would be like somewhere 30 degrees latitude or something, because that looks, sorry, no, maybe 60 degrees latitude, because the angle from the celestial equator to the zenith is pretty big. First, you have to know where your celestial equator is, and then if you have a star, you'd go degrees up from the celestial equator. That could be kind of confusing. Here, the illustrator has screwed up, and if they claim that this is the spring equinox, but they're measuring right ascension from the spring equinox this way, seen from north, that is, wait, is that clockwise or counterclockwise? Let's go. Yeah, that's clockwise from north. So dummy screwed up. The actual direction to measure right ascension would be all the way around, counterclockwise and back, because we measure right ascensions eastward from the spring equinox. Easy to screw this up. Okay, let's talk a little bit about timekeeping. And I want to talk about the motion of the sun through our local sky. The sun follows a kind of interesting path where it travels the ecliptic throughout the year. And if you look at the picture that we had before, if the sun is traveling along the purple line, then what that means, and let's use yellow for the sun because everyone likes that, okay? So here's my sun. And each day the sun is moving like 1 degree along the ecliptic. And as it moves along the ecliptic, it sits in one place, and Earth spins for a 24-hour period. Some days it's here, some days it's there. But what would the path be like through our local sky? The trick is to know what the celestial equator is doing in your local sky, and then to kind of follow the path of the sun on that date. So here's a diagram that would show you the path of the sun at 3 different days throughout the year. Let's see here. Just a moment. I have a good picture of this somewhere. Come on, baby. Maybe I need to full screen this. There we go. Let's try slides 21 and 22. 22 has the same orientation as our picture in the classroom. So here's our north celestial pole up here. And here's our celestial equator there, okay? On the day of the spring equinox, or the fall equinox, the sun travels the path of the celestial equator. So it will rise in the east. It will come up to you know where in the south, and then it will sink down into the west, always on the celestial equator. Each day after the spring equinox, the sun will travel a little bit along the ecliptic, and each day it will travel higher and higher on an equal ring until it gets all the way up to the summer solstice. That's the sort of most northern that the sun will be in our sky. On that day, it will rise north of east, travel up to a maximum altitude of, we're going to solve that later, and then it will set somewhere north of west. And then it will wind its way back down day after day until it's the fall equinox. Then it will travel the celestial equator again. On the winter solstice, it'll rise south of east. It will reach some maximum altitude in the south and set there again. This is a slightly nicer illustration, but this one projects north at an angle, but it kind of shows you the path of the sun traveling along those 3 paths. So the sun mostly travels through the south in our local sky, but its height in the south can sort of depend upon, what day of the year it is. We can predict the trajectory the sun will take through our sky based on its declination, all right? For instance, if the declination of the sun is 0, what day is it?
It's either spring or fall.
Very good. It's either the spring. Don't say spring or fall. That's ambiguous. Say the spring equinox or the fall equinox. Spring is like the whole season, right? Okay. That's right. It's either the spring equinox or the fall equinox, those 2 days of the year. And those days it will travel the celestial equator. And its trajectory would be the same, right? So we'll do this kind of quick, but I want to get this into your notes. What would be the path of the sun on the spring or fall equinox? In the Rhode Island local sky? The answer would be same as the celestial equator. It would rise due east. It would reach 48 degrees in the south, and it would set due west. We could also imagine the path of the sun on some other day. If we did the sun on the summer solstice, it would rise, let's see here. North of east. By the way, what would the declination of the sun be on the summer solstice? I'm going to start using all my vocab now in an effort to twist you around and confuse you. We're going to play 3-card Monty with vocabulary. What would be the declination of the sun on the summer solstice?
23.5 degrees.
Positive 23. That's right. The angle between the celestial equator and the sun at maximum is positive 23.5. Very good. So that means on the day of the summer solstice, it would rise north of east. It would come up to a maximum altitude. I guess the maximum altitude would be this angle plus that angle. Anyone know what that is? Let's look at the other picture for inspiration, because that has it in the same orientation. Okay, so here's the celestial equator. And I know this angle is what?
48 degrees.
That's 48 degrees. And I know this angle is what?
42 degrees.
42 degrees. Wait, no, sorry. No. The angle between the celestial equator and the zenith is 42 degrees, right?
Oh, yes.
But that's not the angle between the celestial equator and the sun on the summer solstice.
23.5.
That's 23.5. So if I add those two together, what do I get? Use your Casio if you can't. Huh?
71.5 degrees.
Right. So on the summer solstice, the sun would rise north of east. It would reach 48 degrees. Let's remember how we did that. Plus 23.5 degrees is 71.5 degrees in the south. And then where would it set? Just so that I know you're with me. I need a new marker here. Where would it set, friends? Where would it set?
Due west.
Not due west. Definitely not. Because look, if you say due west, let me show you.
On the equator, yeah.
That's due west, right? But our sun would be setting over there, which is what?
North of west.
North of west. The reason why I have to say north of west is kind of complicated. This has to do with three-dimensional geometry. An angle that goes from here to here on a curved surface, that might be 23.5 degrees, right? But, okay, let me try this again. This angle is 23.5, but this is also an angle which is not, it's longer than 23.5. This is a triangle on a curved surface for which you must use the spherical law of sines. Sorry, kids, that's over your pay grade. You haven't earned the right to do spherical trigonometry yet. So whatever. Anyways, my point is we'll just loosey-goosey it and we'll just say north of east here and there it's north of west, okay? I wanted you to understand that there was something going on there. Cool beans. You're using the horizon system and the equatorial system in cahoots with each other, and our brains are percolating, okay? Now,
So I have a question.
sure.
So for the winter solstice, the rise and the set, so would it be south of east and south of west?
Yep. And if you want to be a real badass, you can tell me the altitude of the sun at its highest point on the winter solstice.
Just 23.5?
Nope.
Okay.
Because this is 23.5 here.
So
But
48 minus 3.5.
yeah, this is 48, right? So you got to do 48 minus 23.5 or
24.5.
24.5. Very good. So I don't know, today, are we halfway between, if the winter solstice is December 21st, right? And the spring equinox is March 21st. We're really close to February here, right? We're, I don't know, a week from February. I don't know. I'd say we're somewhere in between that right now. In fact, if we knew the declination of the sun, we could actually do it quite specifically. That's what's cool about the declination, right? If I were to, for instance, look up that same ephemeris from last time, sun to Sedna, I could quickly discover that the sun has a declination of minus 18 degrees. So it'll rise south of east today. It will reach a maximum altitude of, you know what to do, right? Minus 18. So I would do for the maximum altitude, I would go 48 minus 18. 30 degrees. Hey, what time is it now? Oh, it's 12:26. So it's roughly noon. So the sun should be about 30 degrees in our southern sky. Maybe I should look out the window here and see what's up. Oh, well, I'm in downtown, so there are all these buildings. I have a very narrow window of Stonehenge there pointing towards the southern sky. So really close to noon, I can sort of see the sun come through the buildings for a minute. Okay, cool. Look, let's talk a little bit about how one would keep time based on the sun. And there are many different ways to keep time, but we, human beings, for the most part, we keep solar time because we're sun-like creatures. We're part, well, we used to be part of an agricultural society. Now we're part of some machine society that doesn't grow our own food too much unless you're a farmer in the Midwest. But for the most part, we use solar time. And solar time is time by the sun. There's actually two different ways to keep time by the sun. There's something called apparent solar time. And apparent solar time is basically time by a sundial. A sundial will track the motion of the sun through your local sky. It does so. Let's look at a pretty picture of a sundial, because everyone likes the pretty pictures. But doo-doo. Let's see here. Oh, where do I have this? Oh, yeah. So here's a beautiful looking sundial. The trick is to make this stick, which is known as the gnomon, okay? You've got a gnomon, and the gnomon will point towards Polaris. And if the gnomon points towards the North Celestial Pole, as the sun travels through your southern sky, it will cast a shadow, which will advance along the sundial. And the way you do things with apparent solar time is whenever the sun is on your, let's see, it rises at the east, you call that 6 a.m., right? When the sun is its highest point overhead, you call it 12 noon. And when the sun is setting on the west, you do 6 p.m. So if you kept time by a sundial, it would always be 6 a.m. at sunrise, and it would always be 6 p.m. at sunset, roughly. I'm pretty sure that's correct.
Yeah, I'm from Colombia, so that's every time.
Pardon?
I'm from Colombia, so the sun always sets. The sun sets is at 6, and the sun rises at 6 too.
What is the latitude of Columbia? Do you know?
Oh God, no.
I mean, we can find out in about 10 seconds, right? We could look up Bogota or what's your? Well, I know how.
It's Barranquilla. I don't know if you know how to spell that, but Bogota is fine. That's the capital, and that's.
Sorry, which one? What should I look up?
Okay, so it's BARRANQUILLA. AN. There we go. That one.
Columbia?
Oh, you go back. Okay. Delete one more space. And it's that one, Barranquilla.
Oh,
The-
sorry. I understand now. Cool. Oh, wow. Right. Because who are you? Who am I talking to right now? Because I don't see you. Or do I see you?
Mateo.
Huh?
Mateo?
Mateo. Hey, Mateo. Listen, Mateo, think about this. You're so close to the equator, right? That yes, it's 6 a.m. to 6 p.m. Because let's take a look, since we have some friends who are not native Rhode Islanders, then what I want to do is take a look at what it would look like close to the equator, okay? Because that's one of the goals that I have for today. For you, the celestial equator is almost perpendicular to your meridian. So I have a picture here of the equator view. Yeah, slide 49. For you being, now you're at 11 degrees north latitude, but that's wicked close to the equator, right? So basically your celestial equator is east to west, and it almost cuts through your zenith. So yeah, your sun is either traveling just, you know, like it's always rising real close to east and setting real close to west. So you're having a full damn close to a 12-hour day, no matter how you cut it. It probably changes by a tiny bit, but it must seem really dramatic to you being in Rhode Island.
Oh, yes. It's horrible.
Right. And for us, that seems normal because we kind of grew up here. Although I remember when I lived in Tucson, when I went to college in Tucson, that's 30 degrees. So that was kind of like, whoa. But for us, if we went to like Scandinavia or Finland, that would seem really crazy because the days get more and more whacked out the farther you get towards the North Pole, right? In fact, on the North Pole, here's some food for thought. There's only one day per year on the North Pole. That's how fucked up things are, right? On the North Pole, like try to imagine what a year is like on the North Pole. I have a picture of that too. Where am I here? Okay. On the North Pole, on the day of the spring equinox, on the North Pole, the celestial equator is your horizon. And to understand how totally fucky-wucky that is, on the day of the spring equinox, if you're on the North Pole, the sun actually just travels the horizon and it's 24 hours of dusk. And then each day you slowly see the sun orbiting the sky, winding its way higher and higher until you get up to spring equinox. And then, sorry, until you get up to the summer solstice, excuse me. That's when the sun is 23.5 degrees above your horizon, and then it winds its way back down, and on fall equinox, there's 24 hours of dusk, and then boom, it's 6 months of nighttime. So
parents are from Estonia, and whenever we go to visit family during the summer, it's like 11 o'clock when the sun sets.
oh my gosh, yeah, that's so whack, right? That's cool. Okay, so I always forget, you know, one of the things I love about teaching at CCRI is there's such a diversity of students who come from all these different backgrounds, and it's one of our strengths, and it's something to celebrate. It's really cool, and especially for having stuff like that going on. Now, in Columbia, it might make sense actually to keep time by a sundial. You know, that's how people used to do it back in the good old timey good days when you kind of just lived in your town or village and you didn't travel too far. But one of the things that you quickly start to realize if you keep careful track of the sun is, was that slide? I already forgot what slide that was, 30, 20, all right. The sun does not travel at the same rate throughout the sky during the day, or throughout the year. The sun actually travels at a different rate throughout the sky, but also you can quickly see that the sun's not going to have the same length of time up in the sky. For instance, you could say that on the spring or fall equinox, the sun might be pretty close to a full 12-hour day, right? But if your path through the sky is shorter, you're not going to be up for a full 12 hours. And if your path through the sky is longer, you're going to be up for more than 12 hours. Close to Columbia, I agree with Mateo, would probably seem close to 6 and 6 each day, but the more north you get, the more wiggity whack it starts to be. And not only is the length of the path different, but the speed of the sun through your sky changes over the course of the year. This happens for 2 reasons. The first is that the orbital path of Earth is not a perfect circle. So when you're close to perihelion, the sun is like moving faster in the opposite direction, and that slows its rate through the sky. And at aphelion, the sun is kind of moving slower, and that speeds it up. Another issue is that even if you're in the summer solstice like this, during the day, the sun has a completely east to west motion through the sky. But on the days of the spring and fall equinox, let's put Rhode Island or America in the center here. The sun's motion has a north to south component, which also slows it down. The result is that if you keep time by a sundial, the length of an hour will vary throughout the year, which is kind of fucked up, right? If you live in a mechanical society and you want people working at the Amazon fulfillment center or whatever, you want to make sure that they're clocking in a full 8-hour day, moving all the boxes around or whatever. So you don't want your shift to depend upon what time of year it is. As we move from an agricultural society to some sort of industrialist society, we wanted the length of an hour to stay fixed, right? And so to do that, we had to kind of invent this new type of time, which was loosely based on the path of the sun, but it actually uses a mechanical clock. And it's something called mean solar time. And that's what we keep. That's what I'm burning through here as I slowly get through my lecture, okay? You keep not apparent solar time. You keep mean solar time. Mean solar time is time by a mechanical clock, okay? And in mean solar time, you have a sort of standard 24-hour day. You try to make each day 24 hours, the length of the hours to be the same. And you can do so by tracking the average rate of the sun through the local sky. That's not as easy as it sounds, okay? Tracking the average rate of the sun through the local sky. Please make a note to self. We keep this time. Let me show you a picture that will help illustrate this point. Since we're using a mechanical watch, if we go out and at exactly noon, we take a photograph of the sun, we will discover that the sun is not always exactly on our meridian at 12 o'clock noon. This is a legendary photograph called an analemma. And the way this picture is taken is some observer goes out and they look south in their backyard and they take a photograph of the sun at exactly noon, well, maybe not every day, but I'd guess there are 1, 2, 3, 4, 5, 6, 7, 8. So that's 16 observations, 30 or so. This person probably went out once every 2 weeks to take a picture of the sun, okay? And they took a picture of the sun every 2 weeks at exactly noon. Remember, the sky is curved, so the meridian is going to look a little weird. But instead of the sun being on the meridian, which if I had to guess in this photograph, the north to south line, the meridian is probably a line that goes like this. Okay, so this line, the red line that I just drew, is the observer's meridian. And what you can see is the sun is either a little bit ahead of the meridian at noon, or it's a little bit behind the meridian at noon by about 20 minutes. And that analemma, this figure 8 pattern, is due to the fact that the sun has a north to south motion during the spring equinox, and due to the fact that the sun travels slower through the sky at perihelion than aphelion. You can use this to create something called the equation of time. Sounds kind of cool, but the equation of time basically just tracks the average rate of the sun so that the sun is pretty close to noon, pretty close to your meridian at noon. And that makes sure that an hour will stay 1 hour, the same unit of time all throughout the year. That's how we keep our time. However, there are other ways to keep time, not necessarily by the sun. For instance, what if I told you that the real spin of Earth on its axis was not 24 hours? What if I told you the actual spin of Earth was 23 hours and 56 minutes? That would probably fuck you up, wouldn't it? It's the truth. There are two types of day. Let's go over them. Okay, so there is a solar day. That's the one that you're used to, a 24-hour day, versus something called a sidereal day. For a little bit of vocab, sidereal means like with respect to stars. So it's a solar day versus a star day, okay? Let's contrast some of the differences. A solar day is a 24-hour day. And it's based on the path of the sun around the sky. It's based on the average path of the sun around the sky. And basically, it's the time from, say, okay, I want to say midnight to midnight, but that sounds like a dog chasing its tail. Let's say we measure the start and end of a day from the Nadir Meridian. Let me explain this. If this is the disk of the ground, and this is the local sky, we call this our meridian. The meridian is the north to south line. But there is another kind of meridian, the one that cuts underneath the ground through the bottom of the celestial sphere, basically the Australia sky or the Indonesia sky, if you want. And that's the part of the celestial sphere that's underneath our feet that we can't see. We refer to this as the Nadir Meridian, and we refer to the top one as the Zenith Meridian in technical astronomy. The zenith is the point overhead. The nadir is the point on the sky below your feet, which you do not see. Now, here's something funky to think about. We start and end a solar day at midnight when the sun crosses the Nadir Meridian, right? Let's draw the path of the sun over a single day on the spring equinox. At midnight, the sun should be at its lowest part of the sky, right? It should come up and cross east at 6 a.m. That's noon. That's 6 p.m. and that's midnight, right? So this is 12 a.m., 12 p.m., 6 a.m., 6 p.m. This is if you're doing, sundial time. Our solar day is the time from the sun crossing the Nadir Meridian back to the Nadir Meridian. I was tempted to say meridian to meridian, but I was thinking that might not be helpful for you guys because that's measuring our day from 12 p.m. to 12 p.m., which is not actually how we do it. Do you see the problem? So if I want to be technically correct, it's the time from the sun crossing the Nadir Meridian twice. That's a little bit awkward, but the time between the sun crossing the Nadir Meridian twice, from midnight back around to midnight. Am I making sense there, or am I confusing the bejesus out of you? Okay, Daniel at least understands me, okay. That's not the true spin of Earth. The true spin of Earth is a sidereal day. The sidereal day is 23 hours and 56 minutes, and the sidereal day represents the true 360-degree spin on Earth's axis. how can this not be the same thing? Because the Earth is drifting around the sun during the course of a day. And that adds to the problem. Let's take a look back here. Okay. The black arrows that you see represent a local observer's meridian line because we're spinning counterclockwise east to west. Remember that Earth, as seen from space, spins counterclockwise, and it also orbits the sun counterclockwise. Let's take a little arrow and imagine that we're in Rhode Island. When it's noontime, our meridian will point towards the sun, not our zenith, but our meridian. And then as Earth goes spinning around the globe, so let's draw some Earths here. So here's an Earth. I should have made it blue, but whatever. Here's an Earth and here's an Earth. Our meridian line will point in different directions. A few hours later, it might point down there. And then a few hours after that, it'll point over here. And then as it keeps spinning, now it'll point over here. And at some point, 23 hours and 56 minutes later, we have completed a full 360-degree spin because we are pointing back and towards the left. Notice, however, that our meridian is not pointed towards the sun because we've moved away from the direction of the sun. We have to spin an extra 4 minutes to point back towards the sun. Now, this may not be obvious to you guys, but this arrow and this arrow both point towards the same star because the stars are so far away that it doesn't matter where in Earth's orbit you are. Anything pointed to the left points towards the same star. This is a geometry problem. Let me see if I can demonstrate it. If you could zoom out to the point where you thought about stars, let's get a star stamp. Here's a star, okay? And now, relative to that star, let's draw the sun. Boop. And now let's draw the orbit of Earth to scale. Boop. Okay, so it kind of doesn't matter whereabouts in our orbit we are. The stars are so far away that whatever part of your orbit you're in, the orbit of Earth is so microscopic compared to the distances to the stars that anything that points towards the left is pointing towards the same star. And what that means is the time it takes a single star to orbit the sky is 23 hours and 56 minutes. The time it takes the sun to orbit the sky is 24 hours because we've pegged our 24-hour day to the sun, right? In other words, if Earth didn't orbit around the sun during a day, if it was stuck in place, but it just spun, then we would have probably defined the solar day as 23 hours and 56 minutes or something like that. Okay, so the solar day is, simply put, the time for the sun to orbit the sky. The sidereal day is the time for a star to orbit the sky. Oh boy, now about to get crazy on you. What if I told you it was possible to measure time by the stars? And that's what astronomers do. This would be called local sidereal time. Can I erase, students? All right, here we go. Introducing some crazy ass shit called local sidereal time. Local sidereal time is abbreviated LST, and it's got a funky definition that's not going to make sense. The definition is the hour angle of the spring equinox. Okay. That probably doesn't make any sense to you. I get that. What it really is time by, well, I want to say stars, but we didn't actually choose a star to track. Instead of tracking a star, we're going to track the spring equinox, which is just as good as any other star because it's a fixed point on our celestial sphere. Okay. I need to draw a diagram, but let's also have a few definitions first. I would like to define the term hour angle. Hour angle will be represented by the letters HA, ha. The hour angle is basically the time since the meridian. In other words, if a star is cycling around the sky, the hour angle of a star is how many hours after it crossed the meridian. So if you're on the meridian, the hour angle is 0 hours. If you're on the Nadir Meridian, your hour angle is 12. What would your hour angle be on the western horizon? Can anyone answer that question? What would your hour angle be on the western horizon? I think we're going to need a diagram for this, but. Anyone?
Would it be 6 hours?
That's right, because it's 6 hours past the meridian. Very good. And so forth and so on. Nicely done, sir. I'd also like to remind you guys that, okay, so by the way, let's, definition. LST, the local sidereal time, is defined as the hour angle of the spring equinox. The hour angle is the time since the meridian. And I want to remind you that last time, because right ascension is going to be a part of this, we defined our right ascension as the hours east of the spring equinox. Right ascension, hour angle, and local sidereal time are all related to each other. But at this point, I think we're going to need a little picture or a diagram to straighten our brains out.
Sure, what does that say? Hours? What? There's a blur.
Oh, so it's glare. It's not blur. It's glare from the computer, I think. Yeah. Hours east. There's nothing I can do here. Hours. Hours east of the spring equinox. I should not use red. The glare is actually coming from my computer, but if I turn the lights up, I think the contrast will get too far. Does that help or does that hurt? I guess that helps a little bit, huh? Hours east of the spring equinox. I need to erase so I can draw a picture. I'm doing that now. Okay, for local sidereal time problems, you must draw a diagram. Okay, this diagram, we're going to start just like our 2D local sky. I want you to make a 10-centimeter line. Mark the midpoint. Draw a dot at the top. I guess I'll use my 3-dot method because that makes a pretty decent local sky with the least amount of effort. I've decided 3 dots is ideal. Just something to help steady your hand a bit, okay? When we do local sidereal time problems, we want to do an east to west diagram, as if we were pointed south in our local sky. Since the sun moves through our southern sky, that's how we want to do things. Stars rise in the east and they set in the west. The observer is here looking south. The line through his head is no longer the zenith, but the meridian.
Excuse me.
Yeah.
Hate to interrupt like this, but I got class in 5 minutes for a
Okay.
different one. You're gonna go over the homework after this, right?
Correct, I am.
And that will be on Blackboard like it was last week.
Yes, it will.
Okay.
Ethan, does that work for you?
Yeah, that's perfectly fine. But you want it in by Sunday at noon again?
Let's just say Sunday. Can I be honest with you guys? I still haven't graded the homeworks. I feel so effing bad about it. But it's not going to take me long to do it. There's been stuff going on and whatever, blah, blah, blah.
No, yeah,
I let you guys
even
turn
had
it in
to
a little
email
late. You can let me grade it a little late. Fair?
No, yeah, I even turned it in at like 7 p.m. on Sunday.
Oh, great. And that's fine. Honestly,
Okay.
what I don't want is I don't want us to get into a big pile up where you guys get screwed. I can grade them quite quickly. So I will try to do that today. I've just had some opening day jitters here. Hey, Ethan, yeah, it'll be posted. This lecture will be posted by 4 or 5 p.m. Just get it done sometime this week. That should be doable, right?
Yeah, easy. Yeah.
Okay, and Sunday is fine. Just anytime Sunday. I know that's a day to catch up on stuff. Yep, I get you,
Okay.
Priscilla. Thanks for being here for part of it, okay?
All right. Yep. Thank
And
you.
we're going to stop lecture soon, everyone else, and we're going to get to homework. So just a sec here. I need to finish this. Then make sure you watch this little bit that you're about to miss.
I will.
Okay, guys, let's quickly draw a star somewhere on our diagram. We'll call it a blue star, okay? By the way, does everyone remember that stars rise in the east and set in the west? If you forgot that, this is the direction in which the sky is spinning, which is why we always have to kind of put east on the left-hand side. This way, the stars are traveling in the direction of a clock. The hour angle of a star is here. It's the time since the meridian. Can anyone tell me what the hour angle of that star is approximately, if you had to guess?
15 degrees.
But we measure hour angle in hours. That's why it's called hour angle, not degree angle. Okay, it's about 15 degrees. So how many hours? Will, are you talking to me or someone else? I don't know what's going on because you're muted, Will.
Sorry, my dad was talking to me in the other room. I'm
Okay,
sorry.
so what's happening is I can hear someone talking and then I can see your mouth moving, but it's not the same people. That's what's confusing to me. So never mind, Will, proceed talking to your dad. Who the shit's saying 15 degrees?
It was me, but I don't know how, like in time. 1 sec. I'm trying to figure it out.
Well, last time we found out 15 degrees was equal to how much time? Didn't we? Okay.
1 hour.
Yeah, okay. Maybe I didn't do this last time, guys. If you spin around the globe, you spin 360 degrees in 24 hours. So if you spin 360 degrees in 24 hours, it's 15 degrees per 1 hour, right? So we're trying to think of this in terms of hours, not in terms of degrees. So the hour angle of this star here would be like 1 hour, right? It's an hour since the meridian. Now, to find the local sidereal time, you would have to know where the spring equinox is. Here's the spring equinox. Can you guys estimate the hour angle of the spring equinox? What would that be? You know that's 0, that's 1. What's the western horizon?
2 hours.
No, 2 hours would be over here.
6 hours.
No, 6 hours would be on the western horizon. You're clearly not in the western horizon. Oh, I'm sorry. It depends which question you're answering. The original question was what's guesstimate the hour angle of the spring equinox?
4-ish.
4-ish. So I would say here, the local sidereal time, we define the hour angle of the spring equinox is local sidereal time. So here the LST would be like 4 hours, right? The right ascension are hours east of the spring equinox, and east means counterclockwise. So from here to here is your right ascension of the blue star. That's the blue star's right ascension. It's the hours east of the spring equinox. Can you guys tell me the right ascension of the blue star? What would it have to be? Here's a hint.
3 hours.
That's right. So here the right ascension would be 3 hours because 4 minus 1 is 3. So we've actually just proven a little mathematical statement that we're going to want for our homeworks today. The hour angle of some random star is the local sidereal time minus the right ascension. There's a lot of different things you can do with this formula, but some people consider it to be the sort of definition of local sidereal time. What it means is a couple of things. It means LST is the hour angle of the spring equinox. But LST also turns out to be the right ascension of a star on your meridian. I'm pretty sure that's how this works.
I have a question. You wrote LST twice in green. I don't know if that's supposed to be the same thing.
It's because I realized I was going to crash into the sky.
Oh, okay.
LST was supposed to represent the green arrow there. So for instance, when the local sidereal time is 4 hours, the right ascension at your meridian is 4 hours, right? Because it's 4 hours there. It's helpful to an astronomer, right? Because if I have a clock with local sidereal time, I always know the coordinates of a star in my meridian, and I can quickly compute how many hours until something like Betelgeuse is rising or setting. It's fucking confusing to learn, but it's easy to use once you're out at a telescope. Sorry about that. Okay, I did not get to every question for our homework today, but I got to most of them, but I am certainly out of time. I'll have to get to the rest of it next time. Yeah, it's 1:02. Humana. So this is where we will sort of end our lecture for today. Although there are other things that I needed to do, but I didn't get to. Sorry, that happens. We're going to do homework next. Today's homework is one of the more intense homeworks we do, only because this stuff, in case you haven't noticed, is quite confusing, right? There's lots of times and 3D diagrams of the sky. This can be some of the hardest stuff in the whole damn class. It's also some of the most useful stuff if you ever want to get your own telescope and figure out what the hell's going on in the nighttime sky. Would you guys like a little pause and a break before we launch into the homework? Because that's usually what I do. I give like a little 5 or 10 minute break just to get some iced tea, something like that. There's only 4 people sharing video with me right now, so let's start with you guys. Are you down with a break? Little pause?
I'll be down with a break, yes.
Yeah, especially because you guys have been interacting with me the way I've been interacting. You've been live, right? So that does take a toll on you. So why don't we say this? It's 1:00 something. iPhone time is 1:04. We'll start at 1:15. Sound like a plan?
Yeah.
All right, I'll see you guys then.
Just one quick question.
Yep.
When I got my materials at the bookstore, like the ruler, the calculator, and all that, I somehow managed to get a protractor.
Very helpful.
So when I'm doing my local sidereal time problems for homework, would this help even though it'll make the diagram look big?
Oh yeah, no, that's a perfect thing. Just, yeah, use that to draw your dome. Go from 0 to 180. Yes. No, that's perfect. That's wonderful. In fact, that's going to be helpful. I should have recommended that to everyone, honestly.
Okay.
So use that baby. All right.
All
See you
right.
guys in 10 minutes. Peace.
Okay.
Okay, students, we're back, and we're going to undergo, or we're going to get going on homework number 2 from chapter S1. If we head on over to our Blackboard, we can find under your astronomy class page, the homework tab, and we're going to be doing this homework. We might want to right click and open up the PDF. So we have our questions handy. Daniel, John, by the way, John, could you rename yourself John? Because
I don't know how to do that. That's
yeah.
from my old label. I don't know what that's about.
I just right clicked your name. It looks like I can rechange you. So I can right click and change your name to John. Okay.
It's supposed to be entheogenic lab. I don't know why it's empty.
Yeah, I don't know either, but it's cool. I was able to rename you just by right clicking your face and choosing rename. I guess that's a perk of running the show here. So Cole, William, John, Daniel, you guys are going to be my readers here. What do we got in the troll factory anyways? What are we looking at here? Oh, we got quite a few trolls floating around in the background. Like I said, guys, if this is acceptable to me, and I like doing the thing live with you guys, but if it gets to me talking to black boxes, then we're going to just watch the pre-recorded videos, because what's the point, right? But the engagement has been good so far, so I'm happy now. But I also know, because I've done this before, I know that as the semester goes on, more and more people stop engaging with me. Hopefully going back in person will fix that. Okay. Let's get our board queued up here, and we're going to set things up exactly the same way we did last time. We're going to have our names, okay? AS1010 section, whatever your section is, 1002. Night class is 101, I believe. So just put one of those. This is homework number 2. Don't forget to label that. And from chapter S1, what are our numbers, students? Too slow.
38,
Oh,
41,
yep.
47, 51, and 53 A to C.
All right. Daniel, I'll ask you to do chapter S1, number 38. What's the title?
Opposite rotation.
Okay, read it away.
Suppose Earth rotated in a direction opposite to its orbital direction. That is, suppose it rotated clockwise as seen from above the North Pole, but orbited counterclockwise. Would the solar day still be longer than the sidereal day? Explain.
Okay, so they want to know, is the solar day longer? Which one of these is normal and which one of these is messed up or different?
The spin
The spin is what?
messed up because it's clockwise.
Right. So this is normal, right? This is
My bad, I haven't been on the camera. I'm just like, I have to be really quiet where I'm at right now.
That's okay. I appreciate you chiming in from time to time. Yeah, I get that. I forget that some of you might be at work or some of you might have some other stuff going on, but we're all doing the best we can, I guess. Does anyone think they know the answer before I explain this thing? Why don't we draw a picture? It can be really helpful to either have a compass or a small circle maker. if you had something like this, boy, would that come in handy here. I'm going to draw the sun here. Leave yourself some headroom for this, okay? And then I'm going to draw some Earths. In fact, I'm going to have to erase here. This is our question, by the way. I actually want to erase this because I need some headroom. You guys might want to start yours lower. I'm going to draw a set of Earths. I'm going to draw 5 Earths. Actually, I want to draw 5 Earths after my Earth. Let me try this even lower this time. This is not doing it for me because of the nature of the magic of the marker that I'm using. I need something different. Let me see if this works a little better. No, this isn't good either. Okay, you know what? Fuck this, I'm freehanding it. Here's the sun. And here's Earth. Honestly, not too bad. I'm gonna draw a bunch of other Earths. 1, 2, 3, 4, 5. Screw it. Okay. In the first diagram, I will draw a line pointed towards the sun, which represents noon. This is a local observer's meridian. The orbit of Earth is counterclockwise. The spin must be clockwise, which is in this direction. I'm going to try to draw the arrow in quarter turn increments. So the next quarter turn, my meridian arrow is pointing up because I'm spinning in that direction. After that, I point towards the right. Then I point down. The next quarter turn should point towards the left, but between pointing down and between pointing towards the left, I will have to rotate through the sun. One of these numbers, 1, 2, 3, 4, 5, represents the sidereal day. Which number represents the sidereal day?
4.
No. What's the definition of the sidereal
5?
day? Why 5? Why 5? What's the definition of the sidereal day?
23 hours.
23 hours, 56 minutes.
What's the next definition?
The true 360-degree see, time for a start. Let's see, 360
The
on
true
Earth.
360-degree spin of Earth.
Yeah.
That's why this is the sidereal day, because it's a full 360 spin. Right?
Mm-hmm.
That's a 360 spin. Which one represents the solar day? Which one represents the solar day?
That would have to be 4, right?
That's right. Why?
Because it's not a true 360 spin.
But neither are any of the rest of those. That's not good enough. What makes 4 a solar day and not 3, which is also not a 360-degree spin? 3 is 270.
Hours.
Huh?
It's gonna take 24 hours for the solar day to go around the.
No, it's not.
Oh,
It crosses the Nadir Meridian twice.
Or in this case, the Zenith Meridian. That arrow represents the Zenith Meridian. If you're a dude standing on Earth right there, it's noon because the sun is over your head. Because this is when the sun is on your meridian, and now the sun is pointing back to your meridian. That's what makes it a solar day. How does this answer our question? This diagram better be included in your answer, by the way, so be writing that down.
So the solar day isn't longer than the sidereal day.
If there was opposite rotation. Hey,
Yeah.
bonus points. Who's talking to me right now?
Cole,
Cole, can you tell me how long the solar day would be?
22 hours?
Not 22 hours. Cole, would the length of the sidereal day change in this case?
No,
So what would the sidereal day be?
24 hours.
False. That's not the
That's
true
the solar
360.
day.
Huh?
The 24 hours that Cole mentioned was the solar day.
Right.
Oh,
The real solar day, the old solar day.
yes.
They did not say that the rate at which Earth's spin changes. They just said the direction changes. Assuming the rate does not change, it should still take the same amount of time to complete a 360 spin. The amount of time it takes Earth to complete a 360 spin is what?
2356.
Good. So what would the solar day be in this case if you had to take a guess?
Just a normal 24 hour.
No.
Oof.
Clearly 4 comes before 5. It has to be shorter than 2356.
Oh yeah, you're right. I'm not sure.
Well, in this case, maybe you should have drawn the regular one, right? In the regular one, you have sun and Earth. And Earth rotates up and it completes 360 first. And then it turns a little bit more to get back to the sun. That's because it's spinning that way, counterclockwise in the normal situation, right? If this is normally 2356 and the solar day is 2400, when it has to rotate an extra 1 degree, it's about 1 degree.
So it's just 4 minutes then.
So
If
the
it's-
solar day in our novel new case would be
4 minutes less.
so
2352.
there you go. All right, you got there.
Eventually got there. Nice.
Well, the diagram helps. The moral of this story is draw a fucking diagram. Diagrams take the CPU load off your brain and they help you understand what's going on if you make your diagram carefully and neatly, which we kind of did. In reality, this has been exaggerated because the Earth only moves about 1 degree in its orbit per day. How do I know it's 1 degree per day? I don't know. It's like 365 days a year, and it's about 360 degrees. And that's approximately 1 day per degree or 1 degree per day, however you want to look at it, right? Anyways. Okay, let's answer the question with a paragraph. That should be part of the diagram, should be part of your answer. And the next thing that I write should be part of your answer. I want to spell that out for you. Yucky.
So the first sentence should be something like, no, the solar day would not be longer than the sidereal day.
Yeah, but let's do it the old-fashioned way they taught us to do in like grade school, where we start by regurgitating the question, right? So we'll say, if the Earth, but yes, you're right. If the Earth were to spin clockwise while continuing to orbit counterclockwise, and now we'll kick in with Daniel's idea, then no, the solar day would no longer, oh shit, I don't want to say no longer be longer, so that's too weird. I want to say would not be longer, okay? The day would the solar day would not be longer than the sidereal day. In fact, as I think Cole might have pointed out, sorry, in fact, the solar day would be 23 hours and 52 minutes long, 4 minutes shorter. Let's explain why, because that was part of our question. Don't forget, we have to answer all parts of the question in our answer, like good little boys and girls. And it said, would the solar day still be longer than the sidereal day? Explain. So here we will explain. This is the hardest part. This is because, does anyone think they can explain why using, here's a hint, use some vocabulary to do this. Can anyone explain why it's 4 minutes shorter based on your, basically you're trying to translate the diagram into words.
Speaking of the diagram, I wasn't able to copy that down entirely. So was anyone able to before?
I wish you would told me that.
Yeah, I was about to. I got some of it down, but I just am missing the.
I should have done this from the first get-go here. You draw the Earth, and then you draw 1, 2,
5,
3, 4, 5 Earths. And then you draw an arrow representing the observer's local meridian. Oops. And then we want to draw it. Whoa, is that an arrow? That looks like a weird ass arrow. Oh, okay, that's better. Undo. And then we draw it spinning, right? So we're spinning clockwise there, and then there, and then there, and then we point back to the sun, and then we point over here. That was basically the diagram.
Okay,
and we
cool.
label, right?
Mhm.
So who can explain what's going on here? John, what's up with that cat? Who's that
I
guy?
know, you jumped on.
That's cool. We like it when your cat jumps. See, your cat is participating more than the average student in this class. What's your cat's name, John?
It's my roommate's cat. His name's Charles Manson.
Charles Manson. I love it. Helter Skelter. All right. My girlfriend's cat has been floating around here. Did I show that to you guys before? Did I show you guys Phil?
Yeah, we saw it the first day.
He's cute. I'm here by myself and he's chilling over there on the mat. He's normally begging me for food all the damn time. So I was thinking like he must know I'm teaching class because he hasn't tried to beg me for food during class, but it's gonna be funny if he does. All right, well, we like Charles Manson. He's welcome to participate anytime. Meanwhile, who's going to explain why the solar day is now shorter than the sidereal day?
You said it was because it's like 1 degree less, right? And that 1 degree translates to 4 minutes. And since it's not a full 360 spin, it's 4 minutes less than the sidereal day.
Yeah, but I like everything you're saying, Kolb, except it. What is it? This is what we want to put our finger on. What is the it that's spinning less?
The Earth.
Well, how do you measure the spin of Earth? You have to have a reference point. The reference point is the arrow. How do we describe the arrow?
It was began with an N, the Nadir thing, equator.
No, the arrows. Yes, it does begin with an M.
Meridian?
Meridian. The meridian is the it. The meridian points to the sun before it completes a complete 360 orbit. That's the trick. Okay, so let me show you how to do this right. Okay, this is because a local observer's meridian will point back to the sun before completing a 360-degree spin. Whereas pointing back to the sun is the solar day, and completing a 360-degree spin is the sidereal day. That's how you answer this question like a boss, okay? Like a boss. Using your vocabulary, making a diagram. This is a picture-perfect answer. In fact, I like this answer so much, I don't even want to read anything else except for this answer. So I'm ready to move on when you guys are ready to move on. That's 38. What their primary role is. Unfortunately, first day of work, this field is not visible to anybody. But you can see that there's a number of fields you can cherry pick. Find nothing here. And so there's nothing confidential. The most personal, obviously, would be your cell phone. So, but you probably already tried it out for to Carney, and that's in your Outlook profile. And so you come here and filter it. So there's I think some shared views here. So for example, new hire list aim. You can see here sort of this from higher date role or bench Are we ready to move on? I'm going to erase. William, chapter S141. Can you read that to me?
Yes, just give me 1 sec.
Title: Fundamentals of your local sky.
Answer each of the following for your latitude.
What's our
A,
latitude?
um,
42.
Wasn't it 41? Or
how would we know that?
Because I told it to you in lecture last time and this
42?
time.
Oh, yeah.
42? It's
wasn't it
42.
41?
Oh, look at that kid. Hey, what's up? What's up, dude? Charles Manson.
Isn't it 42, Professor?
42 degrees north. Okay, what does A ask? Will, you're the reader, right?
Yeah, sorry about that. I said, where is the north or south celestial pole in your sky? That's A. I guess we'll focus on that first.
That's right. And since you're north, we're north celestial pole. So how do we describe the position of the north celestial pole in the local sky? Psst, we did this already today. Better get a diagram here.
Yeah, I'm a little stumped in this one, but I do remember this.
We did this.
Yeah, I know.
Was it an altitude of 42 degrees and an azimuth of 0 degrees or just north?
That's beautiful. That is absolutely beautiful. Function F5, 48. Yeah. Oops. Today, Today, we use the horizon system to recognize this angle as 42 degrees. That's the altitude. And the direction is north or 0 degrees because the closest azimuth is there. Okay, very good. We'll put the technical azimuth in parentheses, 0 degrees. B, Will, read it to us.
Describe the meridian in your sky, specifying at least 3 distinct points along it, such as the points at which it meets your horizon and its highest point.
In other words, we want a rise, a reach, and a set. And we want 3 points for rise, reach, and set. Well, we want altitude and azimuth for each of those, right? Let's start with the rise. All right, can someone tell me where the meridian is on this diagram? Can you draw? Do I allow you to draw on this thing? Someone try to draw. Do I have to give you permission?
Yeah, I don't know.
No, you can annotate. You guys should be able to draw on this. Choose annotate and start drawing. Show me where the meridian is.
I don't have an option to do that.
I have one down like on my little, it goes mute, video, security, participants, chat, new. Oh, there you go. All right, Daniel, show me where the meridian is. Daniel, can you use your purple pen and draw the meridian for me? I guess you could tell me where it is too with words. Does anyone know what the term meridian means? Oh, snap. See, I thought I was talking to some enlightened students here. Nice, Daniel. Very good. Nina. I don't. Oh, weird. Oh, I see. Okay. Hey, Daniel. Yes. So Daniel, why don't we talk about our 3 points then? Okay. Our 3 points should be, let's choose blue, I guess. The rise, the reach, and the set. I need the altitude of those 3 points.
Sorry, I can't draw and speak at the same time.
Speaking is fine. We don't need to draw anymore. You correctly identified the meridian.
All right.
Why don't we start with this point right here in the north?
Mhm.
What's the altitude and azimuth of that point?
I think we kind of did this slightly differently, if I recall my lecture notes, which I have.
We did that for the celestial equator.
Oh, right.
Now we're talking meridian.
Yeah. Right. Okay. So would the altitude in that case be 0 degrees?
That's right, because it's on your horizon. And what would the direction be?
North.
Very good. The technical azimuth of north is, of course, 0 degrees. How about the reach? Altitude and azimuth of the reach.
Would that be 90 degrees?
Which coordinate is 90?
The azimuth, or no, the altitude?
Right, because if you measure the altitude, you're going up from the horizon. Oop. Yep. Good. So what about the azimuth?
Undefined.
Oh, who said that? You smarty pants. Who said that?
Michelle.
Damn, Michelle, that's right. Michelle can see that there is no one point on the horizon that's closer than any other. Look at that. All points on the horizon are equally distant from the zenith. So the azimuth breaks down at the zenith. Very good. So we have 90 degrees. Okay. We could write over here, it's at your zenith. We could also say that this is due north. How about the set point?
Zero degrees due south.
Good. What's the technical azimuth of south?
180 degrees.
Nice. And yes, that is due south. So in a literary way, the zenith rises due north, crosses your zenith, and sets due south. That's also using the it's using the horizon system. Okay. Part C. Moving right along as quick as we can. William, that's supposed to be your job, right? You're the reader.
Oh, cool. I'm the designated. Okay, cool.
For this problem.
Oh, yes, of course. For 41C, it says describe the celestial equator in your sky, specifying at least 3 distinct points along it.
This shouldn't be too hard. We have a rise, a reach, and a set. Altitude and azimuth. Hit me.
So the rise is 0 degrees altitude.
Yeah.
And the azimuth is due east, so 90 degrees.
Very good. So 0 degrees, we'll say east, or 90 degrees, due east. Keep going.
The reach is 48 degrees. And the azimuth is 180 degrees.
or south.
So yeah,
And the
And-
set?
0 degrees and 270 degrees, which is due west.
Lovely. And we did that quick because we already did this in class today.
Yes.
So I'll review that portion of our lecture if you can't remember why we did that. I'm erasing. D, William.
Does the sun ever appear at your zenith? If so, when? If not, why not?
What do you guys think? Yay or nay?
Would it be in the summer because the sun is the longest out, like the highest?
Well,
it doesn't.
Mateo, you're from Columbia, right?
Yeah.
So I'm going to forgive you for getting this one wrong because from the Columbia local sky,
I mean, it's always
it sure as hell will reach your zenith.
okay. So not here.
Oh my God, hold on. There's some crazy person outside. Someone's about to get a piece of my mind. All right, there's some crazy drunk screaming in the streets. Love downtown life. Okay, I'm sorry, I got distracted there. In Columbia, maybe, but let's take a look at a Rhode Island local sky. Our north celestial pole is here. Our celestial equator is there. What is the angle between the celestial? We should know from our previous question, what is the angle between the south and the celestial equator?
48 degrees.
Good. And what is the greatest declination the sun can have above the celestial equator? The sun doesn't just wander anywhere it wants across the globe. It travels the path of the ecliptic, which is tilted to the celestial equator by, well, anyways. What would this angle be between the celestial equator and the maximum altitude of the sun?
71.5.
Well, yeah, but hold on. You're jumping ahead for, this is 23.5 degrees. That's
even like the whole thing. Oh.
And so now if we want to talk about the whole thing, on the summer solstice, as you were originally suggesting, the highest the sun could ever get in the Rhode Island sky is 71.5 degrees. Hey, Mateo, how far north do you think you could go on Earth and still have the sun reach your zenith?
Oh, God.
Maybe a picture would be helpful here. How far north? Clearly, if you're on the equator, the sun will cross your zenith.
Yeah.
If you're in Columbia, 11 degrees latitude, the sun will cross your zenith. How far north can you go and still have the sun cross your zenith?
$23.5.
That's right. Otherwise known as the Tropic of Cancer.
So Miami, basically. Like,
Say that?
like near Miami, like, because I know.
Yeah, I think Miami might actually be 30. Well, actually, no. It's parts, if you get down to like Key West and stuff, it starts to get tropical. They call Florida subtropical. The point I'm trying to make is the tropics run from 23.5 degrees south to 23.5 degrees north. That's the Tropic of Capricorn and the Tropic of Cancer. And those are places where the sun actually crosses your meridian. And for that reason, they're wicked fucking hot, right? So in Rhode Island, we're too far north. No. The sun will never cross, no, not our meridian, but our zenith. The sun will never cross our zenith in the Rhode Island local sky, but only reach a max altitude of 48 degrees plus 23.5 degrees, 71.5 degrees south at noon on the summer solstice. So, Matteo, one of my ideas about liking to teach astronomy in Rhode Island is there are not many good things about doing astronomy in Rhode Island because it's cold, rainy, and wet, and also cloudy 2/3 of the time. But it is nice that we're about 42 degrees is roughly halfway up the globe. So we represent a good arbitrary latitude to imagine the path of the sun. The equator is an extreme and the North Pole is an extreme.
You ready for part E?
Hell, you know I am.
What range of declinations make a star circumpolar in your sky?
Okay, this is tricksy, so we're gonna have to erase here, okay? I need this whole board for this. We're looking for a range of declinations of circumpolar stars. Now, a definition of circumpolar stars is they never rise or set. And I want to show a picture from the book here. How should I do this? There's a picture on page 24 of your textbook that I think is really lovely here, showing some circumpolar stars from the Grand Arches National Monument. And the clever photographer has done this thing where they're like showing the arch and they've got Polaris in the center. And they've left the shutter on for a long period of time so that the stars are kind of rotating around Polaris. But you can see that there are circumpolar stars here inside the arch. The stars outside the arch are clearly not circumpolar because they set below the horizon. Let's keep that handy. Let's look at our local sky here. We have to find the range of declinations, and that might be kind of tricky. Okay. Is Polaris circumpolar? Cole says yes. And circumpolar stars will be close to Polaris, right? These are our circumpolar stars. Let's think about declinations. We have to superimpose declinations onto this. So what would the declination of the celestial equator be?
Would be 0.
That's right. What's the declination of the North Celestial Pole? Sometimes I use delta for declination. Looks like a little musical note.
It's degenerate or? Right?
Nope.
Oh,
Not
9 then?
positive 90.
Yeah.
Because it's your degrees above or below the celestial equator. Here's some tricksy stuff. What would the declination of your zenith be?
45.
Not 45. In Rhode Island, it would be this angle, degrees up from the celestial equator.
42 degrees.
That's right, your latitude. Okay. Polaris, everyone agrees, is circumpolar. We're looking for a range of declinations from what to what, right? So we know that the declination should go from something to some minimum value to some maximum value. And Polaris is the maximum declination a star can have, so it should go to positive 90. The question is, what is the last star, which is circumpolar? Take a look at our picture again. The last circumpolar star is like that one. What's the last circumpolar star doing that no other star is doing?
Making a full circle.
Well, they're all making a full circle. What's this full circle? Why is this one different than the other full circles?
Smaller.
No, it's bigger, actually.
The one that you're pointing at.
The one, all right, these are not circumpolar stars, right? This is the biggest circumpolar star. Or the circumpolar star that's the last circumpolar star is the one with the biggest circle, but it's also the one that does what?
Is in the horizon.
Which direction? That horizon has a particular direction. How would I know the direction here? How would I know which direction the camera is pointing?
To north.
Yeah, because that's the North Star. It's the one that grazes against your northern horizon. So in other words, the last circumpolar star is the one that is going around Polaris, but just grazes against your northern horizon, right? What's the declination of the northern horizon? 0 degrees here, 42 degrees here, positive 42, right? Positive 90. Yawns are contagious through Zoom, apparently. Okay.
Would you add 23.5 to?
No. That's not how this works. Declinations are measured from the celestial equator. You're getting messed up because it's tilted. What's the declination of the red ring?
$12.
No. Declinations are measured in degrees. Okay.
Oh, yeah, sorry.
The red ring is the celestial equator. You just, a second ago, we learned that that's 0 degrees. The north celestial pole is positive 90, right? The zenith is positive 42. But look, you measure up from the celestial equator, right? The blue ring would be like positive 60. The purple ring would be like, sorry, let's try that again. The blue ring would be like positive 30. The purple ring would be like positive 60. The declination of your northern horizon is its degrees above the celestial equator. You know that the angle between the North and Polaris is what? The altitude of Polaris is equal to your latitude.
42 degrees.
So what should the declination of your northern horizon be?
$48.
Good. That's the range of declinations. Hey, Mateo. How do we say the name of your hometown again? Oh, he's not listening. Whatever. Part F. Read it to us, William.
What is the range of declinations for stars that you can never see in your sky?
I call these anti-circumpolar stars. There are parts of the celestial sphere that a Rhode Islander never gets to see. These are stars which are centered around the south celestial pole. They go roughly from here to here. And those stars never get to rise above our horizon. What would be these two declinations here? This is the min, and this is the max for anti-circumpolar stars.
Negative 23.5 degrees.
Careful, no. These angles are determined by your latitude. This is the south celestial pole. You should be able to figure out the declination of the south celestial pole, keeping in mind that you measure from the celestial equator.
So that'd still just be 90 degrees.
But it's negative 90 degrees. Declinations are measured plus or minus from the celestial equator. So this is minus 90. And what would this angle be here? You should know this from your alpha, beta, delta, gamma, delta game.
42 degrees.
No,
48.
that's right. It's south to your celestial equator. It's alpha in the diagram. So it's negative 90 to negative 48 degrees. Let's study that. Okay, I'm erasing. John, will you read?
I'll read, let's see.
47.
47. All right, lost at sea.
Ooh.
During a vacation, you decide to take a solo boat trip. While contemplating the universe, you lose track of your location. Fortunately, you have some I can't say that word for some
Astronomical
tables and instruments, as well as a UT clock. You thereby put together the following description of your situation. It is the March equinox. The sun is on your meridian at altitude 75 degrees in the south. The UT clock reads 2200. All right, so what is your latitude and how do you know?
altitude, John, altitude. Okay. This is the time at the prime meridian. That's your universal time. Let's draw a diagram here. Draw a 10-centimeter line, mark the midpoint, make yourself a dome. Draw a boat. Make the mast point towards the zenith. Make this north. Make this south. Put some happy waves. The sun is on the meridian, 75 degrees in the south. So I'd say 75 degrees is like what? 45, 50, I don't know, maybe like this. If I had a big protractor, I could measure it. I'm guessing this is close to 75 degrees. Question A. What is our latitude? Can you guys figure that out? What's the significance of the spring equinox? Charles Manson, do you know why they told us the sun is on the spring equinox?
Uh, the spring equinox is a moment in time,
Yep.
and it's also a point in the sky along with it's a point on the Earth's orbit.
Right. So in other words, where is the sun on the spring equinox? Let's see here. Can someone show me where the sun is on the spring equinox on this diagram?
I don't know how to edit, but it's like that black dot closest to us.
Okay. In other words, I'm going to say something that sounds kind of funny, but is true. On the spring equinox, the sun is on the spring equinox, right?
Yes.
On the spring equinox, the sun is on the spring equinox. But also what that means is that the sun is on the celestial equator. Wait a minute here. Come on. Now, they told us that the sun is not only on the spring equinox, but that's also on our meridian at an altitude of 75 degrees, right? So that also kind of tells us the local time. So the spring equinox tells us that the sun is on the celestial equator. The fact that they told us the sun is on the meridian tells us what the local time is. What's the local time? Really? The sun's on the meridian should tell you the local time. We
Oh,
now
it's 0 hours.
say that
0 hours. Just
0 hours is midnight.
Oh, then no.
Last time I checked, when the sun was on the meridian, it wasn't 0 o'clock.
Noon?
It's noon, 12 o'clock. So if the celestial equator is there, first of all, am I north of the equator or am I south of the equator right now? Is the boat north or south of the equator? If the celestial equator is there, the north or south celestial pole should be 90 degrees with respect to it. Is this the north celestial pole or is this the south celestial pole? You're killing me, guys. You're killing me.
North?
Huh?
You're in the north?
Yeah, this is north. So you're in the north. That's the north celestial pole. So you should be able to tell me your altitude. Sorry, your latitude, because you should know the altitude of Polaris. Question A, what is your latitude? How do you know? Really? I can't tell if you guys are messing with me or not. Doesn't this look like something that we did today? This dead air is bad for video.
Okay, so so according to my notes, it says altitude of Polaris is equal to your latitude.
Right. We did this today, right? Alpha, beta, gamma, delta. The latitude is 90 degrees minus 75 degrees, 15 degrees. And it's 15 degrees north because you're north of the equator or of the celestial equator. If the sun is in the southern sky on the spring equinox, you're in the north. If the celestial equator is in the southern sky, you're in the north. All right, you guys need to work on that. Hey, that's going to be on your exam, and nobody could answer that. Basically, you could not reproduce the alpha, beta, gamma, delta game yourself, and that's worrying me a teensy weensy bit. All right, how about part B?
All right. 47B, what is your longitude and how do you know?
All right, this one's tricky, so I'm going to help you here. Your longitude are your degrees east or west of the prime meridian. Now, the local time is earlier than the time at Greenwich, England, right? I know that just, from living life, if I'm in Eastern Standard Time, I'm 5 hours earlier than London, all right? In fact, if we're 71 degrees west, remember that you have to use the fact that Earth is spinning about 15 degrees per hour, right? So if you figure your hours off from England, that tells you your degrees off. For instance, 22 hours minus 12 hours gives us 10 hours. If you multiply by 15 degrees per hour, the hours cancel, giving you 150 degrees. Are we currently west or east of the prime meridian? Here, I use the same knowledge I use for Rhode Island. Rhode Island is 5 hours earlier than London, and we're west. So since you're also earlier than London or Greenwich, you're also west. What's part C say?
Part C says, consult a map. Based on your position, where is the nearest land? Which way should you sail to reach it?
A couple of different ways we could do this here. I know. Let's just type it into Google, right? Normally I'd have you use a globe for old-fashioned sake, but 15 degrees north, 150 degrees west. Boom. Thank you, Google Maps. Oh, look, they even have a picture for being lost at sea or something. Okay. Huh. Looks like our nearest hope for land is to go northwest towards Hawaii, because this is north, right? Oh, sorry. North is in that direction. West is in that direction. So part C. Sail northwest. Jesus. Sail northwest to Hawaii. Okay. Number 47 down. I'm erasing. All right. For chapter S1, number 51, we're going to need some new skills that I didn't quite cover in class. I'm probably just going to have us do part A and part B. This is about sidereal period versus something called a synodic period. And sidereal period will be abbreviated as P subscript SID. Synodic period will be abbreviated P subscript SYN. Let's take a look at my slideshow for a second. Earth makes a different orbital period around the sun than the other planets. I think I have a picture of this somewhere. Come on, baby. What the hey? I guess I can do slide 13. The orbit of Earth, as you know, is about was exactly 1 year around the sun. Okay. The planet Mars has an orbital period of close to 2 years around the sun. In 1 year, Earth goes all the way around the sun, but Mars only goes a portion about halfway through its orbit. Then Earth continues to travel for another half a year, and it will actually line up with Mars before Mars completes a full 360-degree orbit. The problem is if you're in an Earth-based reference frame, this configuration is what we call opposition. When Mars is in opposition, it's opposite the sun. And if you imagine drawing in your sort of horizon line from Earth, when Mars is opposite the sun, it's going to cross your meridian at midnight. It'll rise at sort of 6 p.m., cross your meridian at midnight and set at 6 a.m. When you go back into alignment with Mars, it's in the same configuration with respect to the sun. It's opposite the sun at midnight. And that gives you the illusion that Mars has completed a journey around the sky. But it actually hasn't. It's only realigned with Earth. So there are two types of periods. I'll probably have to do this better next time. The sidereal period is the true 360-degree orbit of a planet, whereas the synodic period is the time to align with Earth and the sun. And they're not the same because Earth keeps catching up to the planet if it's an outer planet. You can calculate the relationship between the two using geometry. I'll spare you the details and I'll show you the formulas. The formulas are different whether you're an inner planet, which includes Mercury and Venus, or if you're an outer planet, such as Mars, Jupiter, or Saturn. Outer meaning outer to Earth. For inner planets, the sidereal period is the synodic period divided by the synodic period plus 1 year. For outer planets, the sidereal period is the synodic period minus 1 year. We can go over this more carefully next time, but this is one of the things I didn't get to. Honestly, you just have to kind of plug the formula in. The trick is all periods must be measured in years. In other words, everything's got to be converted to years before you use these equations. John, put a thumbs up when you're done writing. All right. So let's look at the problem here. For 51, use each object's given synodic period to find its orbital period. Why don't we just do A and B? For A, they want us to do it for Saturn, whose synodic period is 378.1 days. For B, they want us to do it for Mercury, 115.9 days. I'm erasing this. A, Saturn. They give us a synodic period of 378.1 days. We cannot use 378.1 days because all units need to be in years. This sounds like a job for what technique?
Dimensional analysis.
Who said that?
Michelle.
Okay, Michelle, why don't you show them how it's done? Why don't we read
So-
our steps of dimension? Are you the Michelle that took my 1020 class, or are you not? Which Michelle are
Yeah,
you?
that's me.
I can't see you because you're hiding.
Yeah, yeah.
Okay, Michelle, read your 4 steps of dimensional analysis. You should know this, by the way, but
Yes.
let's say you're a little rusty in the saddle. Why don't you just
It was
regurgitate?
4 years ago I took that class in my defense.
Okay, all right, that's fair.
But it's so we take the 378.1 days,
We write that
and then
down.
we're gonna do multiplication and the division bar.
Good. That's step.
On the bottom is gonna be days, and on the top years. And we can plug in our the conversion rate. Is that the word?
Yeah, conversion factor. So we cross
Conversion
out
factor.
days.
So 1 year to 365 days.
Here, I've got a small issue with precision.
Okay.
This number has 4 sig figs. If I use 3 sig figs, I will pollute my measurement with a conversion factor, which you never want to do. Now, I know that it's roughly 365.25 days per sidereal year. So let's use 365.25. I want more precision in my conversion factor than I do for my measurement. So
Okay.
punch that in, and how many sig figs are we going to keep in our answer?
We're gonna keep 4.
That's right, because the weakest number has 4. So give me your answer to 4 sig figs.
1.035
Units? Units?
years.
Yeah. So now we've converted our synodic period to years. Now we could use the outer formula planet, which is the sidereal period is the synodic period divided by the synodic period minus 1 year in parentheses. In other words, it's 1.035 years minus 1.035 years minus 1. This is one of those problems where significant figures really matter. I'm going to use my parenthesis keys for this. Everyone watch and learn here, okay? I'm going to do 1.035 divided by, open parentheses, 1.035 minus 1. First, I'm going to close the parentheses, and that gives me the bottom. And then I hit the equals. 4 sig figs. What's my final answer?
$29.57
Units?
years.
Good. Now let's do Mercury. Synodic period of Mercury . 115.9 days. Daniel, show us how we do that dimensional analysis.
Okay, so first we write out the number 115.9
With its units, days.
days. Yes, I was going to say that.
Okay.
Okay, then we multiply by the division bar.
Okay.
Then let's see. Are we going to use the same? What are we going to use the same 1 year over 365.25 days from the Saturn problem?
Yeah, but we always do units first and the conversion factor is second.
So years over days, and then 1 year over 365.25.
That's right.
Okay, it's going to look kind of bunched up on my thing. Then we cancel out the days.
Yep. Punch it up for me, guys. From now on, you do the punching. That's your job. Use your calculator.
Okay. 0.317 years.
That's only 3 sig figs. I want 4.
Okay, 0.3173.
That's right. Okay, now we plug it into our formula for the inner planets. The sidereal period is the synodic period over the synodic period plus 1 year. 0.3173 years over 0.3173 plus 1. Use your parenthesis keys. Divided by, open parenthesis, 0.3173 plus 1, close parentheses, and then equals. What do you get? You guys should be punching. Everyone punch.
Okay.
0.2409
Yeah. Units?
years.
Box it up. That's a classy move. And we'll call that done. No part C. Last problem. Oh God, it's 2:40. This homework is really tough. It takes a little while.
All right, I'll read that. I'll read that one.
Please, and let's get going on it.
All right, so this one, so the title for this one is the local sidereal time one of the local sidereal time formulas that we read in class. The hour angle equals local sidereal time minus RA.
Can I tell you my nickname for this formula? Ha equals list minus raw. That's how I do it, okay? All right, game part A.
Okay, it is 4 p.m. on the March equinox. What is the local sidereal time?
Let's see. On the spring equinox, the sun is on the spring equinox. Strange but true. So how does that work here? Let's draw the diagram. So over here, I'm going to make a little local sky. This one will be 40 centimeters. Make a little tiny one. Fungal here. Okay. We have to do east to west for local sidereal time. That's your meridian. This is east to west. I'd say if it was 4 p.m., the sun was about, 2/3 of the way down, maybe about here. Do you guys know what PM stands for?
Post meridian or afternoon?
Yeah, in other words, if it's post meridian, PM tells you the hour angle of the sun, right? AM is anti-meridian, right? 4 hours is the hour angle of the sun. Because it's 4 hours since the meridian. The local sidereal time is the hour angle of the spring equinox. And there's two ways to do this. One is to ask, what would the right ascension of the sun be? How do we define right ascension again? Look up the definition of right ascension, please. It's my mouse here. What the
Or
shit?
east of the spring equinox.
Say that?
Right ascension is hours east of the spring equinox.
How many hours east of the spring equinox is the sun? On the spring equinox.
0.
That's right. The sun and the spring equinox are in the same place.
Yeah.
So the sun is like here. It's on the spring equinox, right? So the two ways to look at this is the right ascension of the sun is 0 hours on the spring equinox. That means the spring equinox is there. And the LST is the hour angle of the spring equinox. So it's the hour angle of the sun. In other words, LST is Ha plus Ra. The Ha is 4 hours. The Ra is 0 hours. So the LST is just 4 hours. In other words, not only is that the sun, it's also the spring equinox. How about part B? Daniel?
Part B, the local sidereal time is 19 hours, 30 minutes. When will Vega cross your meridian?
Okay, to do this problem, we need Vega's right ascension. Vega's a famous star. The book gives it as 19 hours. Sorry. I think the book gives the right ascension of Vega as 18 hours and 35 minutes. It's actually a little different than that. It's drifted by a bit. I don't know if that's proper motion or if that's precession. Let's take a peek at the star Vega. Oh, wow. 18 hours and 37 minutes is what they have here. The book gives it as 1835. Let's make it hard. Let's do 1837. Why not? Okay. The hour angle will tell us where Vega is on our local sky. If we solve the hour angle of Vega, it's going to be LST minus RA. We should stack them up. The LST is 1930. The right ascension is 1737. Now, I don't know if you guys can do this in your head, but I have a rule, which is I always keep my hours and my minutes separated, okay? And then I try to glue them back together. For instance, 19 hours minus 18 hours is positive 1 hour, but 30 minus 37 is negative 7 minutes. So how do you What do you get if you do positive 1 hour minus 7 minutes?
You get 53 minutes.
Yeah. And that means the hour angle of Vega is 53 minutes, but that's not the answer to the question. If the hour angle of Vega is 53 minutes, that means Vega crossed your meridian roughly an hour ago. But their question is, when will Vega cross next? So if Vega is over here and it crossed 53 minutes ago, it'll take 24 minus that to get all the way back around. So Vega will cross next at, I'm getting out of space here, 24 hours minus 53 minutes. Okay, I need some board space back. Let me erase and kind of continue on back up here. This is part B continued. It'll be 24 hours. Do you guys know how to do this? Let me show you a little trick here. We could switch this to 23 hours and 60 minutes. Then we don't have to deal with any negatives. 23 minus 0 is 23. 60 minus 53 is 7. That's when Vega will cross next. Last problem. And then we're done this epic homework. I'm erasing down here now.
All right. Okay. All right. So the last problem, part C, is you observe a star that has an hour angle of 13 hours when the local sidereal time is 8 hours, 15 minutes. What is the star's right ascension?
Okay, let's have you guys take the lead on this. Can you solve that equation for right ascension? Here's a hint. Add RA to both sides and subtract hour angle from both sides. I'm waiting.
Would it be 2115?
Oh, I was thinking we could write it symbolically first. The right ascension is the local sidereal time minus the hour angle. Local sidereal time is 8:15. The hour angle is 13 minutes. What did you say?
I got the wrong. I added them instead of subtracting.
Look, if you add right ascension to both sides, the right ascension goes away. If you subtract hour angle from both sides, the hour angle goes away there. Right ascension is LST minus ha. 8 minus 13 gives us what?
-5
Hours.
Yes.
15 minus 0 is positive 15 minutes. So what do you do if you have -5 hours and you add plus 15 minutes?
You get -4 hours and 45 minutes.
Very good. One problem though. Right ascensions are usually measured eastward from the spring equinox. The negative means it's being measured westward. To convert to a proper RA, subtract 24 hours. 24 minus 445 gives you positive 20 and negative 45, and that will equal 19 hours and 15 minutes. That's the eastward right ascension, which is what we want. Right ascension shouldn't be negative, in other words. And that, my friends, is a wrap. No doubt about it. Today's homework was pretty epic. All right, I'm going to get processing this video because it took a while. I'll see you guys. Please get these in. I promise I'll do some grading. And I guess I'll see you guys next Monday, right? I'll send out the link around 11:30 a.m. Night, people, get this stuff into me by Sunday if you can. And I'll see you guys later.
All right, have a good weekend.
You too.